All right, so let's have a look at the Otto cycle, which is a blackboard approximation for how the internal combustion engine works if you have a spark ignition engine or a gasoline engine. So the Otto cycle corresponds to a spark ignition, ignition engine. In other words, gasoline engine. So if you have a gasoline engine in your car, chances are you can approximately model the process, the cycle that goes on within the engine, within each cylinder in your engine. You can approximate that as an Otto cycle. So let's talk about the Otto cycle here. So let's put up a PV diagram, and then I'll put up a TS diagram afterwards. So here's a PV diagram, and here is a TS diagram. We'll do them both. Okay. So process. 1 to 2. Process 1 to 2. Let me make sure I start off in the right place. 1 to 2 is isentropic compression, or if you like, adiabatic compression. By the way, if it's adiabatic, you apply the entropy balance, assuming air standard cycle, of course, no irreversibilities within the piston cylinder device, within the system. If it's adiabatic, it also means that it's isentropic. So it's also isentropic compression. So here's state 1 right here. So up to state 2, isentropic compression. Temperature starts initially at T1 and goes up to T2. We're compressing, volume's declining, so temperature goes up. So here's state 2. In terms of the PV diagram, here's state 1. We are compressing it adiabatically, so pressure goes up. Pressure goes up as volume goes down. So here's state 2. By the way, this is volume V1, which is the maximum volume in our cycle. And V2 is the minimum volume in our cycle. You'll see that in just a moment. Okay? So 1 to 2, adiabatic or isentropic compression. Temperature goes up, volume goes down, pressure goes up. Okay? 2 to 3. Instantaneous, instant combustion or heat release or burning of the air-fuel mixture inside the piston cylinder device results in an instantaneous, instant release of heat. The heat gets released so fast that the piston cylinder device isn't moving while all the heat is added. That means it's a constant volume heat addition process. Constant, or if you like, isochoric. Isochoric heat addition. So a spark occurs inside the piston cylinder device. The fuel burns very quickly, so quickly. But as far as the piston cylinder device is concerned, the heat is released instantaneously at constant volume. So if heat is released, temperature and pressure go up. So temperature and pressure go up. So we are adding heat Q in during the constant volume process. State 2 to state 3 is constant volume. And of course, temperature is going up and entropy is going up as well. Why is entropy going up from state 2 to state 3? because entropy brings heat, brings in entropy with it. So we're adding heat, therefore we're adding entropy. Temperature and entropy increase. And then we end up at state 3. So Qn, okay? Qn 2 to 3. Qn 2 to 3. Then we have process 3 to 4, which is adiabatic expansion. If it's adiabatic, it means it's isentropic. Isentropic, so if it expands, temperature falls, pressure falls. So we have falling pressure, increasing volume, falling pressure, adiabatic, therefore isentropic to state 4. Isentropic expansion, temperature falls, no change in entropy because we have no heat transfer down to state 4, okay? Then to get back to state 1 to complete the cycle, 4 to 1, we have isentropic what? We have constant volume or isochoric heat rejection. Isochoric heat rejection. Isochoric heat rejection. Isochoric constant volume, Q out flows from 4 to 1. Temperature falls, entropy falls, heat transfers entropy out of the system because it's flowing out. It cools down and entropy falls. Okay, so this is a PV and TS diagram for the Otto cycle. The PV diagram is nice because it shows you the exact processes. The TS diagram is nice because it gives you an idea of work, cycle work, and efficiency, where the heat addition is occurring and where the heat rejection is occurring. Now let's actually calculate the theoretical efficiency for any Otto cycle. Let's calculate the efficiency for any Otto cycle. Efficiency of an Otto cycle. Let's do that. Now, first of all, let's define a quantity before we get started. I'm going to define a quantity R sub C. R sub C is called the compression ratio. Let me make sure let's get rid of the C. I'm going to be using that for something else. So let's call R is called the compression ratio. It's the ratio of the minimum to the maximum volume in the cycle. So let's go back and look here at the PV diagram. We have a minimum volume at V2 and a maximum volume at V1. And so the ratio of the two, we're calling that the compression ratio. That's going to be an important quantity here in just a moment. So let's make sure we define this. This is the compression ratio. We'll talk about that in just a minute as soon as we get to the actual expression for efficiency. Okay, so how do we calculate the efficiency of the Otto cycle? Well, the definition of efficiency, and this is for the Otto cycle now, the definition of efficiency is the work over the cycle divided by the heat input. Now, excuse me, I can rewrite this on a specific basis. So it's W cycle, lowercase, over lowercase qn, okay? Now the cycle work is equal to the difference between the heat transfer. So W cycle is actually Qin minus Q out. And of course, I'm dividing that by Qn. okay? And you go through and you do a little bit of algebra here, very little. You get 1 minus Q out over Q in. Now let's figure out what these Q outs and Q ins are. By the way, before we get too much further here, we're going to assume constant specific heat for what we're doing to follow. So efficiency of an Otto cycle, and I'm going to put in parentheses here, constant Cp and Cv. So constant Cp, Cv, and therefore K, okay? So the expression that we're going to derive for the efficiency of the Otto cycle is going to tell us exactly how efficient an Otto cycle is. It's going to be assuming constant specific heats, okay? So let's figure out what Q out and Q in are. Let's see here, Q out occurs, so let's have a look at our PV and our TV diagrams. So Q out occurs from state 4 to 1, and Q in occurs from state 2 to 3. Q out, by the way, is out positive, and Q in is in positive. So we have to worry a little bit about the signs here. So Q out is 1 minus Q 4 to 1. And then I have Q in is Q 2 to 3. Why the minus sign in the parentheses? Because Q out is out positive. Q out is out positive from 4 to 1, whereas Q in is in positive 2 to 3. Remember, it's in positive in the energy balance, all right? Okay, so I need to figure out what these heat transfers are. If you like, I'll distribute the negative sign. 1 minus, no, I'll leave it. Let's just leave it. I will leave it exactly the way it is. Okay, so we need to find these heat transfers, Q2 to 3 and Q4 to 1. Let's look at process 2 to 3. If we go back and we look here on our Otto cycle, process 2 to 3 is constant isochoric heat addition. So constant volume heat addition. So process 2 to 3, isochoric heat addition, isochoric heat addition. Applying the energy balance, we have Q2 to 3 minus W2 to 3 is equal to delta U 2 to 3. And if we assume constant specific heats, that's going to be CV T3 minus T2. Okay, so that's Q2 to 3. Now, if it's an isochoric process, what's the boundary work? Remember, this is boundary work. So if it's an isochoric process, constant volume, what's the boundary work? It is 0. So this is 0 isochoric process. So we get immediately Q2 to 3 is equal to CV T3 minus T2, okay? So I get 1 minus so CV T3 minus T2. Okay, so that's the denominator, that's the heat input. You go through and you calculate the heat rejection, you get the same thing. So process 4 to 1. So this is isochoric heat rejection. Okay, and I find that Q, or if you like, negative Q4 to 1 is equal to CV T4 minus T1. Okay, if you like. if you like. And that's out positive. Okay, so the numerator then is CV T4 minus T1. Okay? Now the CVs cancel out, and I get 1 minus T4 minus T1 over T3 minus T2. I got a bunch of temperatures in there related to the heat transfers in and out of my Otto cycle system, my system executing an Otto cycle. Let me do something that might look a little bit strange, but is actually very helpful. I'm going to divide the numerator. I'm going to extract out the T1 and the T2 from the numerator and the denominator, and I'm going to put them in front of the fraction. So I'm going to do 1 minus T1 over T2, extract out the T1 and the T2, and I have T4 over T1 minus 1 and T3 over T2 minus 1. Okay, that might look a little bit strange, but just bear with me for a second. Bear with me for a second. Let's look at the temperature ratio T4 over T1. Let's look at this process 4 to 1. Let's look one more time at process 4 to 1. Again, 4 to 1 is the constant volume heat addition, heat rejection. Constant volume heat rejection. Let's calculate delta S. Let's calculate delta S for process 4 to 1. Let's use a property relationship that involves those natural logs in there for constant specific heat. So delta S from 4 to 1 is CV. So let's look up our property relationships here for constant specific heat. Probably wondering where I'm getting this from. So let's have a look back at our property relationships here. Let's see here. So if you go look for that table, I think it's 6.2. I think it's page 155. No, let's see here. There we go. Delta S, constant specific heat. Here we go. I have a CV ln T final over T initial plus R ln V final over V initial. Okay? So I have an expression here to get delta S, and it involves a change in volume. So let me write that down. So I have delta S from 4 to 1 is equal to CV ln T1 over T4 plus R ln V1 over V4. Okay? Now, this is an isochoric process, so V1 is equal to V4. So this ln of 1 is 0. And so I get delta S from 4 to 1 is equal to CV ln T1 over T4. Okay? Delta S 4 to 1. 4 to 1. I don't know why that says 4. Now, if you apply the entropy balance to process 3 to 2, if you apply the entropy balance, you apply the property relationship for process 3 to 2, you get a similar equation. You get delta S from 2 to 3 is equal to CV ln T3 over T2. Okay? Now let's go to our property, our TS diagram here. Notice that delta S from 2 to 3 is negative delta S from 4 to 1. 4 to 1, 2 to 3. They're opposite each other. So note, delta S 2 to 3 is negative delta S 4 to 1. So this guy is opposite, equal and opposite of this guy. So this implies these temperature ratios are equal and opposite in sign. I'm sorry, these temperature ratios are, be a little bit careful here. This implies T3 over T2 is equal to T4 over T1, since these delta S's are equal and opposite. Okay? T4 over T1 is equal to T3 over T2. That means this quantity in brackets is equal to 1, and it goes away. So I get 1 minus T1 over T2. I'm running out of space here. So I think what I'm going to do is I'm just going to dot, 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 dot. 1 minus T1 over T2, okay? Now, what's T1 over T2? Let's look at process 1 to 2. Let's look at process 1 to 2. Process 1 to 2 is isentropic, adiabatic reversible, therefore isentropic compression. If it's isentropic, I can use a property relationship here. Let's have a look. So isentropic process. For constant specific heats, IGB, isentropic process. So I have a T1 over a T2, which is equal to a V1 over a V2. Let me increase the, there we go. So if I have a T1 over a T2, that means V1 over V2, K, I'm sorry, 1 minus K. That's from the property relationship. That is from the property relationship. So this guy here is really V1 over V2, and then I have a 1 minus K. That's what that temperature ratio is in parentheses. Let me make sure that I have my, that looks good, 1 minus K. Now, I'm going to rewrite this ever so slightly differently. I'm going to take this ratio and put it in a denominator, in a fraction. So I'm going to have, so I get V1 over V2, 1 minus K. And I'm going to put this downstairs in a denominator. 1 minus 1 over V1 over V2, K minus 1. I just took the negative of the exponent and I get a K minus 1. Now, that quantity, V1 over V2, that's actually V max over V min. So let's go back and look at our PV diagram. V1 over V2. So you look at our PV diagram. Look at our PV diagram here. V1 is V max, V2 is V min. So I got the compression ratio down there in the denominator of my fraction. So this guy here is R, or the compression ratio. So I get 1 minus 1 over the compression ratio, K minus 1. So let's write this down here. The efficiency for a Otto cycle, assuming constant specific heats, is a function only of the compression ratio. 1 minus 1 over R, K minus 1. Put a box around that. Put a box around that. So the compression ratio is the only thing that dictates the efficiency of the Otto cycle. So as an engineer, a mechanical engineer, what does this tell you? If you want a very efficient Otto cycle, very efficient engine, so you want to increase efficiency. What do? You have to increase the compression ratio. So you want to increase the compression ratio, or if you like, maximize the difference between Vmin and Vmax. Okay? You want to increase the compression ratio, which is the ratio Vmax over Vmin. Now, for those of you that are motorheads, most gasoline engines, so gasoline engines typically have a compression ratio on the order of around 10, okay? On the order of around 10. The range, older cars are probably around 8, sometimes they're as low. Very old cars from the around the war, the Second World War, maybe 6. Compression ratios have been going up. High performance engines that can run on a high octane fuel. High octane fuel is better for high compression ratio engines. High octane fuel, high compression ratio engines, about 12 or so. Okay, it tops out at about 11 or 12. Now you might ask yourself, why are we stuck at around 10, 11, 12 for a compression ratio? Well, note, as R, the compression ratio goes up, you get what's called pinging or pre-detonation. You tend to get what's called pinging or pre-detonation. Pre-detonation. So it's basically uncontrolled burning of the fuel. If the fuel does not burn nice and smoothly, if it ignites at various locations all at the same time in the combustion chamber, so let's say you've got, so here's our combustion chamber right here. And here's our piston. And we're all the way up at top dead center, or near the top dead center, and you have air, fuel inside. If the air-fuel mixture starts to burn or release heat or explode, if you like, in multiple places, so you've got a flame here, you've got a flame there, you've got flames just spontaneously starting to burn before the spark plug ignites the fuel, pre-detonation. Then these flames grow and they hit each other. The flame fronts hit each other and produce very large pressure spikes. So if you get pinging and pre-detonation, you get large pressure spikes in the cylinder. And those pressure spikes, actually you can hear them, called pinging. The engine will make a ringing sound or a knocking sound. So you get large pressure spikes in the cylinder, and that will do damage to the engine, mechanical damage. So for those of you that think, well, why don't we just keep raising the compression ratio beyond 10 and get efficiencies as high as we like, there are mechanical and engineering reasons why we have not moved much beyond a compression ratio of 10. Direct injection, fuel injection, gasoline engines have helped that a little bit, but we're still stuck at around 10, 11, 12 for a compression ratio for most gasoline engines, okay? Anyway, I hope this has been interesting. We will move on next time to talk about the diesel cycle, which is another cycle commonly used. And then we will move on to open systems, and look at gas turbines, for example. That will be for next time. Take care, ladies and gentlemen.